Hello. Hello and welcome to this program. In this program, we will learn about deadlocks. Okay, um, so where do we start? Now, if you remember my previous video or before that, we talked about something called invariants. Now, every program has some invariants which are supposed to be true at all times. For example, if you have a queue, then the header of the queue or the head of the queue must point to some valid region, memory area, which should point to next node of the same type and so on, or the head can be null. So that is an invariant. Now, as you know, when you will write when you will write a program of queue, it might be the case that queue is pointing to some piece of a memory which is not pointing next to null. Okay. For example, when you insert, the head will initially point to the memory, but the next pointer is not really pointing to the null. And then you have lots of nodes which are actually queue, part of queue, but right now some other pointer is pointing to head. Okay. Or maybe you copied the head to some other variable and then it is pointing to that. But in essence, your queue structure is broken at certain point. For example, suppose you have a binary tree and you are trying to delete a node. So it might be the case that you have copied the predecessor or successor to the current node, but you have not deleted it. That is, the state of binary tree is inconsistent. Now, what could happen is that when you take a lock, certain times one lock will not be enough. You might want to take one lock for multiple locks actually you want to take. Now, when you will write libraries, what will happen is, for example, you are writing a binary tree program to be given as a library. It might be the case that you have mutexes for each node. So that can land you in a bit of problem. Okay, let me show you how. So suppose there are two threads accessing your binary tree code and one does pthread mutex lock on one mutex. Okay, we call it mutex A. And then that thread takes another lock, pthread mutex lock B. Now, suppose some other thread takes a lock like pthread mutex lock and it takes a lock on B first. Okay, and then it takes lock on pthread mutex lock on A. So you see the problem here straight up. So this is your thread 1 and this is your thread 2. Okay, let's suppose this is the order in which they are taking the lock. Now mutex lock is quite an expensive operation in terms of CPU. So it is highly possible that thread 1 takes a lock of mutex A, and before it can take lock on mutex B, thread 2 takes a mutex lock on B. Now thread 1 is stuck trying to take a lock of B, and thread 2 is stuck trying to take a lock of A. This is a situation of deadlock. So we are stuck. So how do we resolve this problem? Let's call this mutex. So there are in general two strategies. One is that there should be a hierarchy of mutex locking. That is, thread 2 should not allow to take lock of B first and then A. That is, the hierarchy should be same. Okay, so that they lock and unlock in a certain order, all threads. That is one way. That is quite possible, and at times it will work. The second way is that you take lock of mutex A, and if you can't take lock of mutex B, you release lock A. You back off from this. You don't try to take, that is, you unlock A. So the idea is you take lock on A. If you can't take lock on B, you unlock A. So that is the second technique. So that way no thread will be blocked in such a manner. Okay. And you can try later also. So this is known as the Backoff strategy. So in this program, we will study deadlock and the uh, Backoff strategy. So first we have a constant here, iterations done, and we initialize 3 mutexes, as you can see in an array. So 3 mutexes are there, Backoff is 1, and yield flag is 0. Okay, 0 means no yield, greater than 0 is yield, and less than 0 is sleep. So let's look at the program, that what it does. So we create 2 threads, forward and backward, and we have a status integer. If argc is greater than 1, then Backoff is we convert ASCII to integer of on argv1. That is, if the first argument is absent or non-zero, Backoff algorithm will be used to avoid deadlock. If first argument is 0, the program will deadlock on a lock collision. Now, if the second argument is absent or 0, the 2 threads run at full speed. On some systems, especially uniprocess, one thread may complete before the other has a chance to run, and you won't see a deadlock or backoffs. In that case, try running with the argument set to a positive number to cause the thread to call schedule yield and at each lock, and make it even more obvious, set to a negative number to cause the threads to call sleep instead. So that depends on our see if that is true, but what we are going to achieve is that we are going to use Backoff algorithm. Okay, so first argument will be absent or non-zero. Okay, so that's what we will do. So here forward thread ID is reserved for lock forward and backward is for lock backward. They're quite similar in implementation. So we look at lock forward first. So as you can guess from the name, it will lock the mutexes in forward order. So it iterates from 0 to iterations, that is done, and we iterate on that, and Backoff is 0. So iterate from 0 to 3, and at I is equal to 0, we take the lock on the mutex, that is the first lock. Okay. Now if Backoff algorithm is in the picture, which will be for our case, okay, psaid mutex try lock will be used. It is not trying to do mutex lock. Okay, if Backoff is 0, then it will do the mutex lock. But we are first going to discuss the Backoff. I think we can simultaneously discuss deadlock and backlog. So if Backoff is non-zero, it will try lock. Otherwise, it will try to lock. Now if status is equal to ebusy, Backoff plus plus. Okay, and then I minus minus to I0 and I minus minus, we do that. We unlock the mutex, and that is what is done in the else case. Now if see that if status is not ebusy and if status is not equal to 0, then we lock the mutex and we got the lock. Now we look at yield flag. So yield flag, where is it coming from? Yield flag is globally 0. Okay, and here we change yield flag on based on the argument count. Okay, so this is we allow the other thread to run it. Okay, we are not going to sleep or something because it has a huge number of CPUs. 24 CPUs is there on this laptop. 24 CPUs are there in this laptop, and that should not be a problem. And finally we unlock all the mutexes 0, 1 and 2, and then we run the thread again. Now sorry, that was wrong. I should be reading here. So the unlock will be in the reverse order. We did lock on 0, 1 and 2, and then we unlock on 2, 1, 0. Now lock backward is similar, but this loop is different here. It is in the reverse order from 2 to 0. So if you see this, it is from 0 to 2 over here. Okay, and this is from 2 to 0, 210. The logic is similar. If I is equal to 2, you take the first lock on the mutex, and if backoff, you try lock, and otherwise status is equal to mutex lock. If status is ebusy, backoff plus plus, and similar logic is there here. So you get the idea what we are trying to do. Okay, so again I will tell you that the first argument is important. So read this before running your code. If the first argument is absent or non-zero, that is, first argument is absent or non-zero, backoff algorithm will be used to avoid deadlock. So first we need to compile that. gcc minus all minus w error minus std is equal to c23 and minus pedantic, so that our program is ISO compliant, and that the file name was backoffstrategy.c. So first argument should be absent or 0. So remember, first argument is absent or non-zero, rather non-zero. So we keep it absent, and you see what happens. Okay, they back off and they try to lock and backing off, try to lock and backing off. So that goes on and on and on. Okay, so you can see the end result here. Lock forward got all locks, 68,581 backoffs. Lock backward got all locks, 160,744 backups. So that is something you can say. Now, what if we make first argument 0? That is, we are going for deadlock strategy. We will no longer use try lock. We'll try to get the lock. And there you go. It got stuck. Now the program won't move forward. It will remain here because both threads are now locked to each other, waiting for the other mutex to finish. So we need to forcefully terminate the program. Okay. So that's the whole idea of that. So once again, I'll repeat that. If you are going to lock in pessimistic manner, that is, you don't want to try lock, make sure this order is same for both the threads. That is, this should also start from 0 and go up to 2, 0, 1 and 2. You shouldn't lock mutexes in opposite order. Okay, you should do that in the same order. That is one way. Or you can do try locking. First you take lock on the first one and then try lock for others, and this should work for you. Okay, but so what can happen is that, this I have said in many videos, now modern CPUs have lots of logical processors. For example, this cheap laptop has 24 CPUs. Servers can have in excess of 256 CPU cores. And if you create threads and you let them have contention for the locks, then the entire efficiency of the multi-thread programming or the advantage goes for a toss. A high lock count is not good for efficient programs. That is why the architecture has changed for last few years. I believe this was all started by SelaDB. They started this, and the framework is C star. Although the technique has been known for a while, C star is what I saw first time sometime around 2014. First time I saw that in production users, you are using HPC kind of technique, thread per core technique. And then many frameworks came up in Rust. I have discussed it: Glomio, MonoIO, CompIO, and then other frameworks like Zitka Web, which have thread per core. So those kind of things are coming up now. So there are several architectures. There is concept of multiprocessor, then concept of worker process, which handles certain number of connections and then they are restarted. For example, that is done in PHP FPM. Worker process serves certain number of connections and they are restarted because or they can have memory leak, so they are restarted so as to release memory to circumvent the problem of memory leak. And the next is the concept of worker process. It takes a connection, offloads to a worker process, and everything runs in a loop, event loop, and that works. So there are quite a few techniques, and as time is passing by, particularly in high processor count, inter-thread message passing is the chosen way to solve the concurrency problem. For example, Rust has MPSC channels, Go has Go routines. So the multiple threads running on the same CPU core with locks and mutexes is an architecture which is not favored. People favor other architectures. One of the bigger problems of this kind of behavior is the debugging problem of the code. Okay. For example, you want to debug this, and let's say 24 threads are running. Then which schedule will get which thread will get schedule when you don't know. And suppose there is some problem in the program logic and you want to debug, but while debugging, the debugger, you will attach yourself to one thread ID, but that thread ID may never get a chance to run with that kind of logic. The other threads won't get a chance to run, and then you're stuck with this notion that, okay, it's just not reproducible. So it's very hard to debug multi-thread programming, and that's why what you should do, I will talk about debugging technique here, is that what you do is you take the thread ID, and with that thread ID you open a log file. So each thread gets its own log file, and they will log their own statements in different log files. That is one strategy I use when doing multi-thread programming. And once you're sure that logic is solid, you can do a conditional compilation with a flag and just do not log it. So in development, you can have a debug switch, and you can turn the switch flag on and log to different files, and in production you just turn that switch off. Okay, so that's how you debug. That's my technique. If you have your own technique, you are free to share with me in YouTube comments. So with this, I will end this video here. I think we discussed quite important aspects of multi-thread programming. And this code, I'll put it in gist. There is no need of gist. It's a fairly straightforward program. So you can pause the video and possibly type it. Or maybe I'll just put it in a gist and give the link in the description. Don't worry about typing it. I'll put it in a gist. Okay, it's not hard to do that. So with this, I will end this video here. And in the next video, we will learn something more about mutexes and multi-thread programming. So I'll see you on the 4th day with another video on multi-threading. Till then, stay curious, keep learning, and most importantly, enjoy.